Alright, this is 15.1, part B. So make sure you look at part A first. So part B is on conservative vector fields. So I'm keeping this separate just because otherwise the section is fairly long. It's more than the average lecture. And so here's a little intro. So until 15.1, you may have thought that we never really saw vector fields before, but we did. We just never thought of them as vector fields. So we have actually seen these before. Seen vector fields before. And in fact, it came up in 15.1. And this is as the gradient of a function. So for example, this is way back earlier in the material. Right? If I have a little f of xyz, is say x squared y plus z, and the divergence of f. Right? So remember, this notation is the divergence of f. So take the partial with respect to x, I, plus the partial with respect to y, x squared j, and the partial with respect to z, k. So this guy right here, this is actually a vector field. Basically, it's the vector field that gives you the direction of maximum increase at each point. Right, so a little note here. This isn't really necessary for what we're doing right now, but this vector field gives the direction of maximum increase of f at each point. Each point, because that's what the gradient does, right? So a vector field that arises this way is very special. It's called conservative. So 2, definition. So in other words, if a vector field is the divergence of a little f, then it's a conservative vector field. So a vector field f is conservative if f is the gradient of little f for some little f. So in this case, there's an addendum definition. So in this case, little f is a potential function for big F, for the vector field. So for example, this guy that we had at the top, if I started with the vector field, if I said big F is 2xyi plus x squared j plus 1k, that vector field is conservative, because that f is the gradient of little f for little f of xyz equals x squared y plus z. So it turns out that conservative vector fields are insanely useful, and we'll see this when we get to integrals of vector fields along curves, right? The conservative vector fields sort of show up as being relevant in a very physics meaningful way. So let's say having a vector field which is conservative turns out to be very useful. It's hard until we get to a later section to clarify why that is exactly. Right now we just sort of have to take it on faith. So as a consequence, if you're just handed a vector field, right, like you might want to know, is it conservative? So consequently, if f is given, how can we know if f is conservative? Like in the previous example, we knew because we started with a little f. But like in this case, i.e., how can we know if little f exists. So knowing whether this exists and then finding it will be relevant, right? So 3, there's a theorem that's associated to this. And the proof of the theorem is well beyond the scope of the course, but I'm going to mention it as a theorem. So the following, let's say, hold. So I'm going to break this into 3 sections. So section A, if f is conservative, then its curl is 0. The proof of this is actually not so hard. So that's the 0 vector. So as a consequence, right, the negation of this, right, so if f is conservative, then the curl is 0, is that if the curl is not 0, the curl is not the 0 vector, then f is not conservative. Now, it would be really nice to have something that says, if the curl is 0, then it is conservative. This actually isn't true, but we can say something really, really close, that if the curl of f, and this is actually fairly intensely difficult to prove, definitely beyond the scope of the course, but if the curl is 0 and big F is defined for all points, then big F is conservative. So we'll actually mostly use just A. I mean, so just to add into this, the part C is not like very rigorous, right? It's actually the case that if the curl is 0, most of the time it's conservative, but exactly what we mean by most of the time is not clear at all. It's not easy to explain what most of the time means. So part A in this case is something we'll tend to use a lot. Right? This is, part B is something we'll tend to use a lot for detecting whether a vector field is not. But I will say this as a little note. So this is a totally informal statement, but if the curl is 0, then F is most likely conservative. For all intents and purposes, we could take it as conservative. So in any case, let's look at an example. So for example, let's say consider vector field F of x, y, z is x, y, I plus x, z, j plus z, k. If we find the curl of this, so remember how this works. I'm going to imagine partial derivatives floating above this. So actually I can do this, let's say this is what I'm picturing in my brain. These 3 guys. I'm going to write them down here, but really I'm just picturing them in my head. And then I'm doing a cross product and taking the appropriate partials. So for the first one we get partial y of z, which is 0, minus partial z of xz, which is x. Now, at this point, we can actually stop, because it doesn't matter what the j and k components are. We didn't get the 0 vector. This is not the 0 vector, because the I component is not 0. So if the I component is not 0, the whole thing's not 0. So as soon as you get something that isn't 0, you're done, right? We'd be like, okay, curl is not 0, not conservative. So here's another example. Consider f of x, y, z equals, say, 2xy I plus x squared plus z j plus y plus 2z k. All right, so here we note that curl of f is, so again, let me write this in pink. I'm picturing these guys. I'm going to take the appropriate partials that come from the cross product. So we have partial y of y plus 2z, which is 1, minus partial z of x squared plus z, which is 1. So that's 0 so far. Then we do partial x of y plus 2z, which is 0, minus partial z of 2xz, which is 0. So far so good. Then we do partial x of x squared plus z, which is 2x, minus partial y of 2xy, which is 2x. Okay, and so we notice this is 0, and because the original f is defined everywhere, right? Every x, y, z. Right? The original f is conservative. Now, so this is sort of step one, because what we're saying is like, well, we sort of have a way of detecting most of the time whether it's conservative. You take the curl and see if it's 0 or not. But this doesn't tell us what the potential function is, right? So down here, we know it's conservative. So there is some little f. With that vector field being the gradient of the little f. But what is that little f? So there are a variety of ways we can approach this. Sometimes we can eyeball it, right? You can look at it and you can sort of make a smart guess. But if you can't make a guess, there's a system that we want. So let me show you just like a really simple one that we can make a smart guess, and then we'll do one in a more complicated manner. We'll do this one that we just did. But first I want to really do a simple one. So let's say finding the potential function. So let's just do two things. A, sometimes we can eyeball it. So I'll show you what I mean by that. Right? In other words, making a smart guess. So for example, suppose that f of xy, I'll just do a two-variable example, is something like, say, 2xy I plus x squared plus 1j. So it turns out that this is conservative. You can take the curl, you can check it. This is conservative. So what is little f? So remember what this means is, right, we want this little f so that big F is the gradient of little f. So in other words, that is the first part of it, the I component, right? This part right here has to be f sub x. And this other part right here has to be f sub y. So in other words, we need little f with little f sub x being 2xy and little f sub y being x squared plus 1. Now, you might look at this for a little while and you might sort of be able to work it out in your head. You might say like, well, like when you look at this, you might think, if I sort of take the antiderivative with respect to x, I get something like this. And here, if you take the antiderivative with respect to y, you might think, well, I would get something like this. And then you might sort of like just chew on those a bit, and you might be like, hey, f of xy equals x squared y plus y works for both. Right? In other words, it works, right? F sub x is 2xy, and f sub y is x squared plus 1. So that's a potential function. Now, that may not work, right? Like you might look at this, you might even look at this one and be a bit confused about what goes on. And even if you're not confused, you might be like, well, what if it's a little more tricky? Is there a system? Is there a systematic approach? The answer is yes. So just for reference, like on an exam, for example, things like that, in the real world, it doesn't really matter how you come up with the potential function if you need to. So, and there are a variety of systematic ways, just for the record. So I just want to give you one, so you have something at your disposal in case you need to use it. Right, so I'll just work through one example, and I'll do this example on the other page, right? I'll do this example right here. So I'm going to rewrite it all at the top of the page. We'll say B, systematic method. So for example, consider the one that just got erased. F of x, y, z is 2xy I plus x squared plus z j plus y plus 2z. Okay, now you may be able to eyeball this as well, and that's fine if you can, that's great. This is just something else to do if we can't just eyeball it, right? So the first time you ever see this worked out, it can be a bit confusing. So sort of follow slowly, go back and watch it a couple times if you need to. I'm going to try and color things in to point to things because I need to cross-reference some things a few times. So I'll try and go carefully. But this is what we're looking for. We want f of xyz such that f sub x of xyz would be 2xy. F sub y of xyz would be x squared plus z. And f sub z of xyz would be y plus 2z. Right, that's what we want. So let me label these, say, A, B, and C. Blue. So the first thing I'm going to do is I'm going to take, and again, there are choices here, but I'm going to follow the same rigorous, I'm going to follow a method that will work all the time when you're looking for the potential function. So from A, this is what we get, right? We have, so f sub x of xyz, I'm going to recopy it. So what I'm going to do is I'm going to take the antiderivative with respect to x. Right? So when we do that, this is what we get. Now, I'm not quite done. You might be like, well, maybe there's a plus c. But here's the thing. There's more than a plus c. Because when you take the derivative with respect to x, all the y's and z's vanish. Which means there could have been any combination, sorry, that's not right, of y's and z's tagged on at the end. So this is the antiderivative with respect to x. And if that's confusing, think if you go upwards, if you start with this f and you take its derivative with respect to x, all that g vanishes and you just get the 2xy. So what this has given us, it's given us a version of f which is imprecise because we've got this g tagged on the end. So then what we do is we take the derivative of this thing with respect to y. So we take f sub y of xyz from here. So what happens is this thing gives us f sub y of xyz is x squared plus g sub y of yz, because we don't know g. But this thing has to equal b, because they're both f sub y's. So this has to equal, let's get the colors all right, this has to equal b. So what that tells us is that x squared plus g sub y of yz that's the thing we just wrote, that has to be equal to x squared plus z. Now, that lets us find g sub y. So we can cancel the x squareds and we just get z, right? So then what we'll do is the following. We'll take the antiderivative of this with respect to y. In other words, the antiderivative of g with respect to y. So this will tell us that g of yz is yz. But then, in this case, there could also be some z's that go away. So like some other function, h of z, which is like a constant in this case. So what we'll do next is I'm going to take this g, and I'm going to put it back into the f that was earlier. So let me label something here. So we're going to take this g, we're going to put it back into here. Let's call this d. So what we'll do is we'll put this back into g, we did in pink, let's make it pink, or into d. And so when we do this, so that d says that f of x, y, z is x squared y plus g, but this is the g. So I'll stop for a second. I just want to point something out here. What happened is we started with, like our first attempt gave us this f right here. And now we've got a slightly better f. So what we'll do next is we'll then take f sub z from here. So what we get is we get f sub, and again, let me use the green. We're doing from here. So we're getting f sub z of x, y, z. So we get 0 plus y plus h prime of z. I can write h prime now because it's just a function of z. And now, but this must equal c. So I have the c back over here. So because they're equal, we know that y plus h prime of z is y plus 2z. So h prime of z is 2z. So h of z is z squared. Now I can write plus c. So now this guy, this goes back into, let me label this pink as well, this guy e. So what we do is we put this back into e. Which we made pink. And what we get there is, we do that to get f of x, y, z is x squared y plus y, z plus h, which is z squared plus c. Now, it turns out that when we're finding a potential function, the plus c won't matter, right? So what that basically means is we're looking for a potential function, any one we want, so we just let the c be 0. So generally for us, c won't matter. So this will be our final answer. And the nice thing about this process is you can check it. But because at the very, very end, if you take this thing, you pick out a different color, purple's good, and you take its gradient, you should get this back. In other words, if you take the derivative with respect to x, you should get this. If you take the derivative with respect to y, you should get this. If you take the derivative with respect to z, you should get this. And then everything works out. So this looks awfully complicated, right? Probably Potentially you'll have to read through it, listen to it a couple of times just to see what's going on, but it works every single time. And then 2 closing comments is, one, if you do this with just an I and a J, it's actually easier because there's no Z's ever showing up, so the process becomes much shorter. And then another thing to consider, which is kind of a fun question, which I like to leave open-ended, is what happens if you start with a non-conservative vector field? Like, this shouldn't work, so it's an interesting question as to where does it go wrong if the vector field is not conservative. So it's kind of fun to try it and see if you can diagnose what the error is. So otherwise, that's the end of that part.